All right, let's take a look at the first problem from our second problem set for Chapter 11. So we're told we have an exhaust stream from a combustion process that contains 10% water vapor by mole. The pressure of the stream is 2 bars, and the temperature is 100 degrees C. What is the relative humidity of the stream? What is the due temperature? And then we'll take a look at C. Okay, and so if we were to start with A, okay, again, what is relative humidity, right? So the idea is that we're going to have equilibrium involving a non-condensable component, right? So if I have an exhaust stream, right, even already here it's suggesting it's air, right? It's going to be a mixture of air with water, okay? So maybe water plus other non-condensables, where it's 10% by moles, so vapor composition of water. And so remember the basic idea again is that at saturation, okay, if component 1 is water, right, Rayleigh law is going to be applicable. So we're going to be at low relative pressure as well, removed from the critical point. And assuming the liquid phase is ideal is going to be a really good approximation because our liquid phase is essentially going to be pure water. Okay, and so what relative humidity is this is the vapor composition of water at saturation, right? Rayleigh's law corresponds to two-phase coexistence. So the relative humidity is just a matter of what's the actual vapor composition relative to that at saturation. How close am I to saturation? If I have a relative humidity of 1, I am at saturation. So then all I do here is for y1 sat, I'm going to plug in p1 sat over p, and I get the following expression. Okay, so the relative humidity is just y1p, my actual vapor composition, times p over p1 sat. Okay, so I would just go ahead and calculate my relative humidity as y1p over p1 sat. Okay, how do I get P1 sat? P1 sat is only a function of temperature, right? I know P1 sat is only a function of temperature. So you can use an Antoine expression for water, or you could go to the steam tables. And what I'd be looking for here is, right, P1 sat is only a function of T. I would look up the vapor pressure at 100 degrees C, right? And it's one of the ones I remember. So, 100 degrees C, the vapor pressure is going to be 1 bar. Okay, but you would go to the steam tables or use an Antoine expression to calculate P1 sat. Okay, and so if P1 sat, if you look it up and it's in fact 1 bar, pressure is 2 bars. Right, so that's 2 over 1 times y1 is 0.1, and then my relative humidity is going to be 0.2. Right, so that tells us it's not saturated. Okay, when I look at B, okay, what does this mean? What is the due temperature? So the due temperature, okay, due temperature will be when our relative humidity equals 1. Just think about dew on a cool summer night. I have a given partial pressure of water, so given mole fraction of water in my air at a given pressure in my hot summer day, right? Then at night, sun goes away, things cool down, and so it's going to lead to water condensing out of my air. So the due temperature will correspond to, if I have a system at a given, relative humidity. So say I have air at this given partial pressure, for what vapor pressure, for what pure component vapor pressure will I have a relative humidity of 1, at which point water will begin to precipitate out of air. Remember, P1 sat is only going to be a function of T. So that's what the due temperature is. Okay, when you think about T, you think about P1 sat. Okay, so I'm going to solve for when the relative humidity is equal to 1. Okay, and then Y1 and P, right, I'm going to assume I have the same exhaust stream as before, which is at a given mole fraction of water and a given pressure. And so what I want to solve for then is I want to solve for the temperature. Okay, so remember P1 sat's only a function of T. The temperature for which the vapor pressure is equal to the partial pressure of water. Okay, so again, so y1 in our case was it 0.1? y1 is 0.1. P is 2 bars. Okay, so P1 sat then. P1 sat would be equal to 0.2 bars. So I'd go to my steam tables and I would search for the temperature at which my saturation pressure is equal to 0.2 bars. Or again, if you had an Antoine equation, you could solve for the T, for which Psat was equal to 0.2 bars. Okay, cool. Okay, but whenever you see T, think of Psat. So basically, if we're at 100 degrees C, so if we're at 100 degrees C, P1 sat would correspond to 1 bar, and we'd find we have a relative humidity of 0.2, I think we said. Okay, and so we know that if we were to cool down the temperature of my exhaust stream, okay, so if I were to cool down the temperature of my exhaust stream, we're looking for the temperature at which water begins to condense out of my air. Okay, cool. Okay, and so we're solving for the temperature at which we could begin to condense water. C. The stream is to be cooled to 25 degrees C at constant pressure. To avoid condensation, the exhaust stream is mixed with dry air prior to cooling. How much air is needed? Report the results in moles of dry air per moles of gas. Okay. So what I'm going to do is I'm going to try and draw a picture to feel my way through this. Okay, and we can start on the next page. Okay, so I'm going to draw essentially a little mixer. It's going to look just like my flash drum. Okay, I'm going to have some inlet stream, which is my exhaust. All right, I'm going to mix my exhaust. Plus, I'm going to have an inlet stream consisting of dry air. Okay, and so when you hear dry air, what that means is there's going to be no water present. Right, so in this case, Y1, let's call this stream, say B, and this stream A. Okay, Y1B is going to be equal to 0. Dry air means no water present. Okay, and then that's going to mix to form our final stream. So if I label my inlet, so again that's 0.10 mole fracs water, pressure of 2 bars, and temperature is 100 degrees C. So this is Y1A was our 0.1. P, I'm going to label this as stream A, is 2 bars. And the temperature of stream A is 100 degrees C. Go back and look at my dry air. So it just says that to avoid condensation, the exhaust stream is mixed with dry air. Okay, and then the streams would be cooled to 25 degrees C at constant pressure. To avoid condensation, the exhaust stream is mixed with dry air prior to cooling. Okay, so I'm going to take it then that we have the stream of dry air, and that our dry air is also at 100 degrees C. Okay, doesn't seem like we're told anything about pressure. Okay, but I'm not sure that we need to know anything about temperature, or not temperature, or anything about temperature and or pressure. All right, so we'll come back to that. Okay, and then we're going to mix those two streams, and actually let's make my picture correct. In theory, well, okay, we can do this. So in theory, it's going to be a box. Okay. Okay, and so then that'll form some exit, some product stream. Okay, and so we're mixing before cooling. So then presumably that would subsequently be cooled or chilled to form our final mixture. Okay, where this final mixture Okay, let's call this stream D. That's going to be at 25 degrees C. Okay. And now when we're told we want to avoid condensation, okay, well, water is going to begin to condense out when I have a relative humidity of 1. So basically I'm going to want a relative humidity then in this exit stream, okay, of say less than or equal to 1, right? But in theory we'll solve for, say, a relative humidity equal to 1 for the purpose of problem solving. And what will happen is, we'll solve for a given amount of dry air to get a relative humidity of 1 at 25 degrees C. Then for relative humidity to be less than 1, you would just add, slightly more dry air. Okay, and so basically we want to mix these so that we end up with a final mixture that has a relative humidity of 1 at 25 degrees C. Okay, cool. All right, cool. And it seems like that's all we are given. Arg. Okay, so, well, what can we do? Okay, well, I'm going to make a couple of assumptions because we're not really given all that much. Okay, as I feel around with this, okay, so I'm going to need some flow rate of A. Okay, I'm going to need some flow rate of B to know how much I'm mixing with A. Okay, so I'm going to assume a basis of A, let's just say 1. Okay, and so I'm going to solve for B, however much B I need to mix with my A stream, so that again, my system has a relative humidity equal to 1 at 25 degrees C. Yeah, and so how I'm going to work with this then is if I want a relative humidity of 1 at 25 degrees C, essentially I'm going to solve for, it's the dew temperature calculation. Okay, but if I want a relative humidity of 1, okay, this is in stream D, well then that'd be Y1 in stream D times P over P1 sat, okay, at D is equal to 1. All right, so Y1D would be equal to P1 sat over P. Okay, now this is where I'm going to need to make an assumption, right? So we were told, not PB equals 0, but PB equals question mark. Here it doesn't really matter. There's no air present, so the partial pressure of water is 0. Okay. But what I'm going to assume here is, since we don't know what the pressure is, I'm just going to go ahead and assume, say, that the pressure is still equal to 2 bars. Okay, because I don't think we're not given one. Yeah, and it says report the results in moles of dry air per moles of gas exhaust. So taking a basis of 1 is going to be reasonable. Okay. So what I will go ahead and do then is I'm just going to assume that the pressure is equal to 2 bars. Okay. So at 25 degrees C, you could look up the saturation pressure of water on the steam tables, or at 25 degrees C, you could calculate P1 sat via an Antoine equation. And so then if I take the pressure to be 2 bars, I can go ahead and calculate Y1D. Okay, so then the idea would be I would know Y1A, I know Y1B, okay, and I know Y1D, so I know the mole fractions of water in all the streams. And then if we assume a basis of A is 1, flow rate of A is 1, or the amount of exhaust gas is 1, basically what we just need to solve for then is FB. Right? Cool. So I'll just write down a mass balance then. So FD, right, would just be FA plus FB. And then I would have, let's see if this will work out. Y1D, which we just solved for, times FD is equal to Y1A times FA plus Y1B times FB. Okay, So where we see if these things work is y1b is 0. Okay. So working with our second expression then, we get that FD is going to be equal to y1a over y1d times FA. Okay. And so y1a, right, we're given the problem statement, that's the 0.1. y1d is the P1 sat d, so that's my vapor pressure at 25 degrees C times P, and FA is just 1, right? So what I really want is FD per moles of FA. So I could go ahead and I could calculate FD, okay, and so that's going to be my final exit flow rate. Okay, then FA is 1, right? So it'd be per mole of exhaust gas. Then I want to know how much bone dry air is needed. Well, FB then would just be FD minus FA. Okay, and I don't have a calculator, so I'm not computing any of these numbers. Okay, but just looking at this, okay, we have y1a over y1d. Okay, so I know that as my temperature decreases, my water is going to be able to hold, less. My air is going to be able to hold less water before it condenses out. Okay, and if I'm adding bone dry air, then composition is only decreasing. So y1d should be less than y1a. Right, and I guess if I look at this, P1 sat's going to D is going to be much less than P1 sat at A. So y1d is going to be less than y1a, and so this term should be greater than 1, so I should get an FD value that's greater than FA. Okay, so that should be it. This would give me how many moles of bone dry air would need to be mixed per mole of exhaust. All right, cool. And then the idea is, ultimately I'm going to take my exhaust and cool it down to 25 degrees C. Okay, and then what I'm computing here is if I were to cool it down to 25 degrees C, I could compute what the mole fraction of water would be at saturation. Okay, and so I want to add dry air so that I could dilute water so that my y1's less than y1 sat at 25 degrees C, right? So that it's not condensing out of vapor phase. Okay, cool.